LLM4Decompile, decompiling binary code with large language models. Abstract, decompilation aims to restore compiled code to human-readable source code, but struggles with details like names and structure. Large language models, LLMs, show promise for programming tasks, motivating their application to decompilation. However, there does not exist any open-source LLM for decompilation. Moreover, existing decompilation evaluation systems mainly consider token-level accuracy and largely ignore code executability, which is the most important feature of any program. Therefore, we released the first open-access decompilation LLMs ranging from 1 billion to 33 billion, pre-trained on 4 billion tokens of C source code and the corresponding assembly code. The open-source LLMs can serve as baselines for further development in the field. To ensure practical program evaluation, we introduced Decompile eval, the first dataset that considers recompilability and re-executability for decompilation. The benchmark emphasizes the importance of evaluating the decompilation model from the perspective of program semantics. Experiments indicate that our LLM4Decompile has demonstrated the capability to accurately decompile 21% of the assembly code, which achieves a 50% improvement over GPT-4. Our code, dataset, and models are released on GitHub. Figure 1. Pipeline to evaluate the decompilation. 1. Introduction. Decompilation is the process of converting compiled machine code or bytecode back into a high-level programming language. This is often done to analyze the workings of software when its source code is not accessible. There have been numerous tools developed for decompilation, such as Ghidra and IDA Pro. Although these tools have the capability to revert binary code to source code in specific scenarios, they often fall short in producing code that is easily readable by humans. The inherent difficulty of decompilation lies in the inability to fully recreate the source, especially finer details like variable names and the primary structure, such as loops and conditional statements, which are often lost during the compilation process. Recent advances in large language models, LLMs, have led researchers to approach programming languages as distinct linguistic systems, using pre-trained code LLMs for various coding tasks. These models have shown impressive performance improvements over traditional techniques, which leads us to the possibility of applying LLMs to cope with the decompilation challenge. To illustrate, transformer-based models such as Slade and Nova have showcased the potential of using language models to turn binary code back into source code that is much closer to the source code in readability and structure. However, the scope of their models is somewhat constrained at 200 mm and 1B parameters for Slade and Nova, which could result in a reduced capacity for learning and generalization, whereas larger models typically exhibit a marked improvement in these areas by leveraging their extensive parameters to process and integrate a broader range of information. Moreover, their lack of public availability limits their contribution to promoting further progress in this domain. Furthermore, to the best of our knowledge, no standardized benchmark dataset exists for evaluating and comparing decompilation techniques. Researchers tend to employ different datasets to evaluate their results, making direct comparison difficult. Therefore, there is a strong need to establish a benchmark to evaluate the decompilation performance, which can significantly facilitate the formulation of coherent and standard evaluation criteria for the decompilation domain. Thus, our objective is to create and release the first open-source LLM dedicated to decompilation, and to assess its capabilities by constructing the first decompilation benchmark focused on recompilability and re-executability. We start by compiling 1 million C code samples from AngaBench into assembly code using GCC with different configurations, forming a dataset of assembly source pairs in 4 billion tokens. We then fine-tune the DeepSeek Coder model, a leading-edge code LLM, using this dataset, following by constructing the evaluation benchmark, Decompile eval, based on human eval questions and test samples. Specifically, we formulate the evaluation from two perspectives: whether the decompiled code can recompile successfully, and whether it passes all assertions in the test cases. Figure 1 presents the steps involved in our decompilation evaluation. First, the source code is compiled by the GCC compiler with specific parameters, such as optimization levels, to produce the executable binary. This binary is then disassembled into assembly language using the obdump tool. The assembly instructions are subsequently decompiled to reconstruct the source code in a format which is readable to humans. To assess the quality of the decompiled code, it is tested for its ability to be recompiled with the original GCC compiler and for its functionality through test assertions. On Decompile eval, the LLM4Decompile models demonstrated promising results in their ability to decompile binaries, with an impressive 90% of the decompiled code being recompilable using the same settings in the GCC compiler, signifying a solid understanding of code structure and syntax. As for the ability to execute the code, 21% of the decompiled codes from the 6B version successfully capture the semantics of a program and pass all the test cases. In conclusion, our contributions are twofold. We provide the first open-source LLM ranging from 1B to 33B tailored for decompilation, which also facilitates compilation and diverse binary tasks. We construct the first decompilation benchmark, which targets recompilation and re-execution rate, which indicates syntax recovery and semantic preservation, both essential for usable and robust decompilation. 2. Related work. 2.1. Decompilation. The practice of reversing executable binaries to their source code form, known as decompilation, has been researched for decades. Traditional decompilation relies on analyzing the control and data flows of program and employing pattern matching, as seen in tools like Hexray's IDA Pro and Ghidra. These systems attempt to identify patterns within a program's control flow graph that corresponds to standard programming constructs such as conditional statements or loops. However, crafting these rule-based systems can be challenging and prone to mistakes as the rules are complex to create, often only partially cover the control flow graph, and take extensive time to develop. They are particularly weak when facing code that has been optimized, which is a common practice for commercially compiled software. The code output from such decompilation processes tends to be a source code-like representation of assembly code, including direct translations of variables to registers, use of gotos, and other low-level operations instead of the original high-level language constructs. This output, while often functionally similar to the original code, is difficult to understand and may not be efficient enough to allow for recompilation. Drawing inspiration from neural machine translation, researchers have reformulated decompilation as a translation exercise, converting machine-level instructions into readable source code. Initial attempts in this area utilized recurrent neural networks, RNNs, for decompilation, complemented by error correction techniques to enhance the outcomes. Nonetheless, these efforts were constrained in their effectiveness. The latest advancements in natural language processing, NLP, have enabled the use of pre-trained language models, LMs, for coding-related tasks. These models generally incorporate the transformer architecture, using self-attention mechanisms, and are pre-trained on extensive text datasets. This approach allows LMs to capture contextual nuances and aids in the acquisition of general language understanding. In the realm of binary decompilation, BTC was one of the first to fine-tune an LM for this purpose. Following this, Slade utilized the BART model and trained an LM-based decompiler with 200 million parameters, while Nova developed a binary LM with 1 billion parameters starting from the starcoder checkpoint and fine-tuned it for decompilation. Although these models show potential in decompilation, they are limited in size, e.g. the Code Llama model launched in 2023 has at least 7 billion parameters. 2.2 Evaluation. There is a notable gap in the field of decompilation, a lack of a unified accepted benchmark for measuring the quality of decompilation tools. Various sources are used for evaluation purposes. BTC, for example, leverages web data including interview-style coding problems and the extensive Debian Linux repository to evaluate decompilation accuracy. Meanwhile, Slade is tested using both Synth, a synthetic code generation framework, and the subset of ExecBench, a benchmark consisting of executable C programs. Nova evaluates its decompilation capabilities on a synthetic dataset that it created, in addition to the CodeFlaws dataset, which is designed to identify common coding errors. The metrics employed for these evaluations predominantly focus on n-gram similarity, with the use of BLEU or token accuracy, as well as edit similarity. Slade goes a step further by incorporating input-output accuracy into its evaluation framework. This metric assesses semantic equivalence through behavioral equality, meaning it checks whether the decompiled code and the original code produce the same outputs when given the same inputs. However, input-output accuracy relies on external processes to generate input and output samples for comparison. The generation of input and output samples often involves randomness, leading to non-deterministic results and making it difficult to consistently assess the performance of a decompiler. Consequently, our goal is to develop and make the first open-source large language model tailored for decompilation. We also aim to establish the first benchmark for recompilability and re-executability to set a standard for performance evaluation in the field of decompilation. 3LM4Decompile. In this section, we describe the pre-training data, present different model configurations, and discuss the pre-training objectives involved in pre-training the LLM. 3.1 Pre-training data. We construct ASEM source pairs based on AngaBench, which is a public collection of 1 million compilable C files. Following the practice of previous works, we first compile the source code into a binary object file, disassemble the object file into assembly code, and pair it with the source code, where we only consider the x86 Linux platform. In the real deployment, programmers will choose different compiler optimization flags to optimize the execution performance. Compiler optimization refers to the process of tweaking and transforming source code to generate faster and more efficient machine code. Figure 2. Training objectives. It involves techniques like eliminating redundant instructions, better register allocation, loop transformations, etc. The different optimization levels trade off compile time against execution time and debugging ability. The key optimization levels are O0 default, no optimization, to O3, aggressive optimizations, compilation time consuming. We compile the source code into all 4 stages, i.e. O0, O1, O2, O3, and pair each of them with the source code. To inform the model with the optimization stage, we use the following prompt. This is the assembly code with optimization state, optimization, SM code. What is the source code? 3.2. Model configurations. Our LLM4Decompile uses the same architecture as DeepSecCoder, and we initialize our model with the corresponding DeepSecCoder checkpoints. As a neural translator, the training objectives can be categorized into 2 categories, as shown in Figure 2. 1. Next token prediction, NTP or language modeling, which is the pre-training objective of most LLM models targeting predicting the next token given previous inputs. As depicted in equation 1, it minimizes the negative log probability for the ground truth token x sub I. See Formula 1, where the conditional probability p is modeled using LLM4Decompile model with parameters theta. These parameters are optimized by applying the gradient descent algorithms with respect to the input sequence x sub 1, x sub 2, to x sub I minus 1 preceding the given token x sub I. 2. Sequence-to-sequence prediction, S2S, which is the training objective adopted in most neural machine translation models that aims to predict the output given the input sequence. As depicted in equation 2, it minimizes the negative log probability for the C-code tokens x sub I to x sub j, see Formula 2, where the loss is calculated only for the output sequence x sub I to x sub j, or the C code. The main difference lies in whether the input sequence or the input assembly code is included in the training loss or not, whereas in language modeling, all the inputs are included for loss calculation. We conduct different ablation studies on these 2 training objectives to explore their effectiveness in decompilation. 4. Experiment setups. 4.1. Decompile eval benchmark. Currently, there appears to be no benchmark for decompilation evaluation that considers whether code can be recompiled or executed correctly. When assessing decompilation model performance, researchers rely on metrics that measure n-gram similarity, such as BLEU or CodeBLEU, or edit similarity, ES. However, these metrics, commonly used in machine translation and text generation, fail to adapt to the evaluation of programming languages. Programming languages are highly structured and logical, insensitive to the naming of functions and variables, yet very sensitive to the flow of data and logic. Changing variable or function names does not affect the meaning of a program, but a single logical error can alter its entire function and purpose. As illustrated in Figure 3, the use of BLEU and ES in evaluating code similarity is problematic. Figure 3. Limitation to use BLEU and edit similarity for evaluating decompilation results. For SARC sub 1, the variation from the original SARC is confined to type conversion of variable num, which leads to high BLEU and ES scores. However, this alteration completely changes the intent of the code. Similarly, SARC sub 2 achieves high BLEU and ES scores, yet the semantics of the function are lost. Conversely, SARC sub 3 undergoes normalization of function and variable names, causing no semantic shift, yet scoring 0 in BLEU against the original code. The example of SARC 4 is more extreme. If the program logic is broken down into multiple lines, the ES drops to 41.4%, falsely indicating a low similarity. However, during compilation, names are typically standardized by the compiler, and source code is often broken down into basic operations depending on optimization. For this reason, the ability to recompile and execute the code is far more indicative than n-gram or edit similarity for evaluating decompilation efficacy. To address the gap in decompilation assessment, we introduced Decompile eval, the first benchmark to evaluate the recompilability and re-executability of decompilation systems. This benchmark is derived from human eval, the leading benchmark for code generation assessment, and includes 164 programming challenges with accompanying Python solutions and assertions. We converted these Python solutions and assertions into C, making sure that they compile with the GCC compiler using standard C libraries and pass all the original assertions. In our evaluation process, the C source code is first compiled into a binary, then disassembled into assembly code, and finally fed into the decompilation system to be reconstructed back into C source code. This regenerated C code is compiled with GCC to test recompilability and combined with the original assertions to check if it can successfully execute and pass those assertions. Recompilability and re-executability serve as critical indicators in validating the effectiveness of a decompilation process. When decompiled code can be recompiled, it provides strong evidence of syntactic integrity. It ensures that the decompiled code is not just readable, but also adheres to the structural and syntactical standards expected by the compiler. However, syntax alone does not guarantee semantic equivalence to the original precompiled program. Re-executability provides this critical measure of semantic correctness. By recompiling the decompiled output and running the test cases, we assess if the decompilation preserved the program logic and behavior. Together, recompilability and re-executability indicate syntax recovery and semantic preservation, both essential for usable and robust decompilation. In alignment with established evaluation practices, following SLADE, we partition 1,000 samples from the ANGA bench into a test set. We then utilize BLEU and ES as our primary metrics for assessment. 4.2. Baselines. To benchmark against SOTA decompilers, we selected two key baselines. First, GPT-4 represents the most capable LLMs, providing an upper bound on LLM performance. As one of the largest language models, GPT-4 significantly surpasses previous LLMs across modalities. Second, DeepSeek Coder is selected as the current SOTA open-source code LLM. It represents the forefront of publicly available models specifically tailored for coding tasks. While recent academic works showcase LLMs for decompilation, these models present significant integration challenges, such as complex preprocessing settings, non-standardized tokenizer model loading, and necessitating significant effort to modify and adapt them. We thus selected GPT-4 and DeepSeek Coder as representative cutting-edge and open-source baselines accessible for evaluation. Table 1, Evaluation Results on Decompile Eval. Table 2, Evaluation Results on Angab and Bayan. 4.3, Implementation. We use the Python implementation of the DeepSeek Coder models, 1.3b, 6.7b, and 33b obtained on Hugging Face. We set a global batch size equals 2048 and learning rate equals 2e-5, and train the models with the AtomW optimizer for 2 epochs. During the evaluation, we set the max new tokens to 512. To ensure fairness in the analysis of time and space complexity, all experiments are performed on a cluster equipped with 8 NVIDIA A100 80GB GPUs. 5. Experiment results. 5.1. Main results. Table 1 presents the primary findings of our study. Initially, the base version of DeepSeek Coder was unable to accurately decompile binaries. It could generate code that seemed correct and was sometimes compilable, but failed to retain the original program semantics. After fine-tuning, the LLM4Decompile models demonstrated a significant improvement in their ability to decompile binaries, with an impressive around 90% of the code being compilable, signifying a solid understanding of code structure and syntax. As for the ability to execute the code, the 6B version of LLM4Decompile shows a remarkable advantage over the 1B version. 21% of the decompiled codes from the 6B version successfully capture the semantics of a program and pass all the test cases, while for the 1B version, only 10% can be re-executed. The improvement highlights the benefits of larger model sizes in capturing the semantics of a program. Nonetheless, the increase in model size to 33B yields only a marginal improvement, with an average increase of less than 1 percentage point in re-executability. This plateau may be due to the challenge of tuning the 33B model. Table 2 summarizes the results on AngaBench, where LLM4Decompile shows notably high BU and ES scores. For example, the 6B model achieves 0.82 BLEU scores, almost identical to the source code. This outstanding performance suggests a significant data leakage issue within the test set. Decompiled code, with its variables normalized, should not realistically allow for such high n-gram ES scores. This anomaly underscores the importance of establishing an independent, reliable benchmark for decompilation evaluation, as similarly high BLEU and ES scores have been reported in prior research. 5.2. Ablations. As discussed in Section 3.2, our LLM4Decompile model adopts a sequence-to-sequence forecasting approach, which outperforms other training techniques for several reasons. In this training methodology, the input, specifically the assembly code, is not included in the calculation of the loss function. This allows the model to focus solely on generating accurate output source code, enabling it to better understand the underlying patterns and structures of the decompiled code. In contrast, integrating the assembly code into the training process, as in the next token prediction tasks, encompasses both the input assembly code and the output source code, which can decrease performance by around 4 points, as shown in Table 3. The complexity of assembly code is another factor. Being inherently complex and low-level, it is harder for the model to learn meaningful patterns when assembly code is included in the training process. Table 3. Ablation study on training methodology. By excluding the assembly code from the loss calculation, the S2S approach enables the model to avoid this complexity and concentrate on high-level source code patterns. Although an alternative strategy involves an initial training step with both assembly and C code followed by fine-tuning focused on the translation task, NTP plus S2S, this approach still doesn't perform as well as the S2S. 6. Conclusions. We presented the first open-source decompilation-focused LLM and standardized recompilability, re-executability benchmark. Analyses on this diverse compiled C code dataset revealed promising capabilities. Our 68B model achieved 87% recompilability, indicating syntactic understanding, and 21% re-executability, suggesting semantic preservation. As an initial exploration into data-driven decompilation, our work establishes an open benchmark to motivate future efforts. The public dataset, model, and analyses represent encouraging first steps toward enhancing decompilation through novel techniques. 7. Limitations. The scope of this research is limited to the compilation and decompilation of C language targeting the x86 platform. While we are confident that the methodologies developed here could be adapted to other programming languages and platforms with relative ease, these potential extensions have been reserved for future investigation. Additionally, our current study is constrained to the decompilation of single functions, without taking into account factors such as cross-references and external type definitions. This presents a simplified view of the decompilation process, omitting the complexities introduced by these elements. Addressing these aspects would provide a more comprehensive understanding of decompilation across a broader spectrum of scenarios and is an important avenue for subsequent research. This concludes the reading of LLM4Decompile, Decompiling Binary Code with Large Language Models on research to you. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.